Which of the following electrophiles would react the slowest in an SN2 reaction? So we look stumped because we're seeing stuff we've never seen before. But the key here is understanding what the leaving group is, right? So we're talking about what's different amongst all of them. The carbon skeleton's all the same, but the leaving groups are all different, right? So that's the kind of the interesting thing here. I'm not asking you to determine which one's going to react the fastest because it turns out 3 of these all react really, really quickly with each other. One of them reacts very slow. So the key here is to turn each one of these leaving groups into a base and then assess the basicity of that, right? And we can do that by pKa value if we want to, but I think you'll see what's going to happen here. So say it again. Is B the word? No, actually it's not B. And I'm going to show you why here in a second. So let's turn this into the leaving group here right now. Okay, so OH2 plus is going to fall off as, you guys are going to know this one, OH2, which you know more commonly as H2O, which, by the way, very, very stable. How good of a base is water? It is the worst base you can think of. Absolutely the worst base you can think of. And the reason for this is because if you think about the conjugate acid for water is H3O plus. This has a pKa value of like -2. So this tells us that hydronium is a great, great acid, which means water must be a really, really bad base. The bad base, it's a good leaving group. He's out. All right, OMS. This is called a methylsulfonic ester. Okay, so what does this look like? So when a methylsulfonic ester falls off, it has the shape that looks kind of something like this, which is a lot like a sulfuric acid, very, very much like a sulfuric acid. And so if you know anything about sulfuric acids, you know that sulfuric acids have pKa values that are well below, not well below, but they're below 0. Point here is that this is a bad base. So since it's a bad base, what does that tell us about its leaving group ability? Great leaving group. Okay, OCH3. It falls off as methoxide. And what have we said about methoxide? Is it a good base or a bad base? It's a great nucleophile. Remember, we talked about this before. Great, great, great nucleophile. So what does that tell us about its basicity? If it's a good nucleophile, it's a good base. So what does that tell us about the leaving group? Think about the logic here. Bad leaving group. This isn't a bad leaving group. This is a horrible leaving group. Excellent base and nucleophile. That's the point. All right. And then finally, we have our last one. Br falls off. We get Br minus. And what do we say about Br minus? Is it a good nucleophile or a bad nucleophile? Well, let's see. Br minus, when converted to the conjugate acid, is HBr, which we said is a fantastic acid. So what is that telling us about Br minus? If HBr is a great acid, what does that say about Br minus? It is a, what type of a base? Bad base, right? So if it's a bad base, it's a great leaving group. And that's the textbook example of a leaving group here. So to answer our question, which one of these is going to react the slowest? D. That's because basically non-reactive in an SN2 reaction, but more to the point, it is a horrible leaving group. And since it's a bad leaving group, it's not going to want to react.